Okay, so today's warm-up is complete review from what you did in 8th grade math, or if you took Accelerated last year, you also saw this. So it's solving systems using substitution. And when we do substitution, what we're doing is we're hoping that one of our equations is already solved for a variable, which this one already is. And so since y is equivalent to x plus 4, wherever we see a y, we could plug in x plus 4. So 2x plus y, which we just decided was equivalent to x plus 4, equals 1. So we get 3x plus 4 equals 1. So 3x equals negative 3, and x equals negative 1. Yay, I'm done. No, I'm not done. I have to plug it back in. Because the solution to a system is the ordered pair that satisfies both equations. So I just found the x coordinate. Now I need to plug back in to find the y. So if I plug in the negative 1, I get y equals negative 1 plus 4, which is 3. So my solution is negative 1, 3. Now solutions to a system must always work for any equation in that system. So if I plug in negative 1, I get out 3. If I plug in negative 1 here and 3 here, does that equal 1? What is negative 2 plus 3? 1. When I plug it back in, it must give me true equations for any equations listed. Does that make sense?
Yes, ma'am.
Okay. So in this second one, it's already solved for y, so I substitute in for y again. Could I have one solved for x?
Yeah.
Sure, and substitute in for x. Okay, so when I substitute what y equals, which is 2x, in where y was, this is the statement I get. 7x plus 10x is 17x equals 34. So x is 2. And when I plug 2 back in, I get y is 4. So my solution is the ordered pair 2, 4, which works here. And if I plug in 2 here and 4 here, I get 14 plus 20 equals 34. Yes, it does. It works for both equations. And they should always work for both. Any questions?
I did it differently, but I still did.
Okay, did you use substitution? Because there are multiple methods for solving systems. You guys learned graphing, substitution, and elimination last year. So today we were reviewing substitution, and then later on this week we'll review elimination. And we're also going to talk about graphing today. We're going to review graphing in class, and then we're going to talk about the application of that graphing. Last year you concentrated mainly on the skill. This year we're going to concentrate on application of that skill. Do you know how to use what you've learned to solve problems? So if we take a look at our new calendar, here they come, you'll see what we're going to do this year. Okay, so if we take a look at the website, and we go to Unit 2, which is what we're starting. Unit 2 is reasoning with systems of linear equations and inequalities. So what we're gonna look at is the idea of adding two equations together as a means of justifying steps to solving simple equations. We're gonna understand the graphing method for solving systems. We're gonna also look at other algebraic methods such as elimination or substitution. And we're going to use those in real-world problems. So here's your calendar, also downloaded to the website. And if we look at the calendar, today we're going to concentrate on graphing, and tomorrow we're going to actually do graphing using technology. So tomorrow, any of you that have a graphing calculator, if you own your own graphing calculator, please bring it to class tomorrow. If you do not, that's fine. I have a class set that we'll be using tomorrow. Okay, but if you have your own, bring it, and then I can help teach you how to start using things on the graphing calculator, because we will be using that technology with our problems tomorrow. We're going to use some tables to solve. We're going to look at elimination and why it's a valid method. Who decided it's okay to add and subtract separate equations? I know you know what to do. You know how to subtract things to make them cancel out. You know how to multiply through to make stuff cancel out. Why is it legal to just add two separate equations together? That's what we're going to talk about on that day. And then the second week, we're going to be using a method called linear programming to solve problems that have multiple restraints, and you're going to find the optimal solution. So when we do that, I will walk you through it on day one, how to set it up, and then on day two, you get more practice. Then we have review, and we have our assessment, and then we'll begin Unit 3 on the 17th. So this is kind of a mini unit because nothing is really brand new. It's just application of what you've already learned. Any questions about the unit? Okay, and do you see there's not even a quiz, is there? It's so short we don't even need a quiz. All right.
I feel like Unit 3 is going to be a really big unit, though.
They do get more exciting.
Exciting.
To me.
Is that types of functions?
Unit 3 is characteristics of functions, and we will study all different types of functions. Yeah, so right now we're just doing linear equations, so those make straight lines, right? And so we talked about the function part. So for a line, that's any line except what kind of line is not a function?
Circle.
A circle is not. That's not a line.
Vertical.
A vertical line. A vertical line is the one line that's not a function. So any vertical line is not a function. But in the characteristics unit, which is Unit 3, we're going to look at all sorts of crazy functions. We're going to look at the one that kind of looks like a parabola, a U. It's called a quadratic function. We're going to look at the one that looks like a V. It's called the absolute value function. The one that kind of squiggles in the middle, cubic. And then we're going to look at just plain old graphs I make up. My favorite one is the one that looks like a W. We're going to do lots of stuff with the W. And so that's what we'll do in Unit 3. And that is where it gets more interesting. I'm with you.
Interesting or hard?
Sometimes interesting is hard. And sometimes interesting is just new and different. Yay! All right. So today we're going back to look at solving systems by graphing. And we're on page 97 in your workbook. So if you have your workbooks with you, please flip to page 97. If you don't, just kind of follow along. And the problems that we do, you do on notebook paper, please. Oh, you can certainly do it in your workbook. Okay, so the essential question, how do you approximate the solution to a system of linear equations by graphing? That's what we're going to look at today. So a system of linear equations consists of two or more linear equations with that have the same variables. The solution of that system is the ordered pair that satisfies both equations. Okay? And we looked at it over here when we looked at this. When we plugged it back in, did it work for both equations? Yes, we checked it off. Yes, it works for both. So it has to work for both equations. The values of the variables in the ordered pair that make the values of the variables in the ordered pair that make each equation in the system true is our solution. Okay, so let's take a look at this first one that they gave us. Example 1. Solve the system of equations by graphing and check your answer. Okay, last week we talked about 3 methods for graphing. Okay, the first one is the oldie but goodie, y equals mx plus b. And this is probably the only one you've really focused on so far. The second method we looked at was using intercepts, finding the x-intercept and the y-intercept. And the third method we looked at was point slope. And for some of you, this was totally new. So by plotting a point and applying your slope when it's given to you in point slope form. Now, here we have two equations. And obviously, it's not in point slope form. So we're either going y equals mx plus b or intercepts. Now, since they're both in standard form, you may have jumped to intercepts. But both of these would also be quite simple to rewrite in y equals mx plus b form. So let's do the first one. We'll do the first one in y equals mx plus b form. And we'll do the second one by doing the intercepts, just to remind everybody. So the first one, negative x plus y equals 3. If we were to rewrite that in slope-intercept form, what's the only thing I have to do? Add x. And when I add x to both sides, it becomes a positive x plus a 3 on the other side. Any questions about how to do that? All right, so let's plot it. My y-intercept is 3. My slope is positive 1. So up 1 over 1, up 1 over 1, up 1 over 1. And guys, you should always check the scale on both your axes. I did this problem last period, so I knew it was counting by 1s on the x-axis and by 1s on the y-axis. So it is just up 1 over 1 when I do my slope. If our scale changes on one of the axes, that also changes how we would have to count out our slope. So once you get a couple dots, you're going to take a straight edge. Most of you may still have that straight edge that came in your agenda. You are welcome to use that one, or any ID you might have, or if you have to, you can use mine out of the container over there by the fan. All right, drawing in my straight edge. Okay, so the second one. Second one we're going to do in intercept by finding our intercepts. X and Y intercept. Okay, so this one we use the little chart for. To find your x-intercept, you plug in 0 for your y. If I plug in 0 for my y, I'm left with 2x equals 6. So what is x? 3. Now to find my y-intercept, I'll plug in 0 for my x. If I plug in 0 for my x, all I'm left with is y equals 6. So 6. So I have an x-intercept at 3, 0, a y-intercept at 0, 6. And then I'll graph in the line. Close, but not perfect. There.
What's the slope of that?
The slope of this line would be negative 2. Down 2 over 1, down 2 over 1, down 2 over 1. So, it looks like it intersects perfectly here, doesn't it? So what is that solution? 1, 4. So if that is the exact solution, then it should work when I plug it back into both equations. So if I do negative 1 plus 4, does that equal 3? Yes. And if I do 2 times 1 plus 4, does that equal 6? Yes. So the point 1, 4 is a solution to the system because it works on both equations. Any questions? All right. So let's take a look at page 99. Example 2, I would like you to try this one. Here's your system. You can pick your method. This one's set up for intercepts, but you can pick your method and graph the system here. Let's see what you get. so in this first one, if I take the first equation and plug in my zeros, I can get my y-intercept is 1, my x-intercept is 2. I put a point at 2, 0, and a point at 0, 1. And then I would graph the line between those 2 points. I'm way off. That looks good. Okay. And now I'll do the next one. The next one was, if I plug in 0 for my x, I get out -4 for my y. If I plug in 0 for my y, I get out 6 for my x. So I need a point at 6, 0, and a point at 0, -4. And then I'll graph in the line. Nice and off again. Let's see if it slides onto it. Whoops. Yeah. Okay. So it appears my solution is right here. Right in there. So it kind of looks like 4, -1, right? All right. So let's plug in 4, -1. I get 4 plus -2 equals 2. Is that true?
Yeah.
Yes. Okay, let's plug in 4, -1. I get 8 minus a -3 equals 12. Is that true?
No.
No. So what does that tell me about the solution? It's not quite right, is it? It's approximately the right solution because it looks like it's really close to 4, -1, but it's not exact. Now, sometimes an approximate solution is good enough. And sometimes in word problems, approximate is good enough. But what would I do to find the exact solution since we know it's not 4, -1? What can I do with this system? What do you think?
Solve it using elimination or substitution.
Solve using elimination or substitution. And I'm going to use substitution since that's what our warm-up did today. If I take this top equation, I can solve for x just by moving the y over. Do y'all see that? And since it's x equals this, where the x was, instead of 2x, I'll put in 2 times 2 minus 2y minus 3y equals 12. And solve this equation. So we get 4 minus 4y minus 3y equals 12. So I can combine and get the -7y. Move the 4 over and get 8. So y is -8 sevenths. Is -8 divided by 7 pretty close to -1? Yeah, so we see how that was a fairly good approximate there. And now I would plug this value in to solve for x. So I get x plus 2 times -8 sevenths equals 2. Do you see how all I did was plug that y value into the first equation? So we get x plus -16 sevenths. 2 would be 14 sevenths, right? And then if we add 16 sevenths, we get 30 sevenths. How many times does 7 go into 30?
Like 4 times.
4 times. Isn't that what we had on the approximate? So there's my approximate. My exact answer is 30 sevenths, comma, -8 sevenths. This is the exact. This is the approximate. We found the approximate from our graph, but this is the exact.
Which one would you want us to put as the answer?
It depends on the directions. And tomorrow, we're going to learn to use the graphing calculators to come up with a decimal approximation for that intersection. So it'll give us, this is the exact, but it'll give us a decimal that's really close to this tomorrow when we use our calculators. Okay. Now, we're going to look at number 1 on, what page is this, 101? No, 102. So if you'll flip over in your workbooks to page 102, we're going to look at problem number 1. Okay, Mr. Malone is putting money into 2 savings accounts. Account A started with $200 and account B started with $300. Mr. Malone deposits $15 into account A and $10 into account B each month. How many months will the accounts have the same balance? And what will the balance be? Okay, so he has two accounts here. He has account A, and he has account B. Now, is there a constant rate of change in this problem? Yes. So we could model this situation with a linear function, couldn't we?
Sure.
We have his account balance, and we can let that be represented by A or B or whatever. The balance with respect to the number of months that he's been investing money. Now, when we write a linear function, we're looking for two things. What is our starting point? Because the starting point gives us what on the graph? The y-intercept. And then we're looking for the rate of change, because the rate of change in our equation is what?
Slope.
The slope. Okay, so for account A, what was our starting point?
200.
200. What was the starting point for account B?
300.
300. Okay. How did account A change?
$15.
$15 every month. How did account B change? $10 every month. So here are two functions that represent this situation. Now, your workbook was really nice for you. They went ahead and gave it a title, which we should when we have a word problem. They labeled the axis. They considered the scale already. Now, the thing about them doing all this is, do you see how they've counted by 2s on your horizontal axis and by 50s on your vertical axis? When they do that, we have to be very aware of that when we're counting out slope. Because if we had a slope of 3/2, could we just go down 1, 2, 3 and over 2? No, because going down 3 really has a value of 150, and going over 2 has a value of 4. 150 divided by 4 is not equivalent to 3/2, is it? So when we have a different scale on our axis, you just have to be careful when you're graphing. So let's graph this first one together for account A. We're obviously going to start at 200, because that's our starting point. Now, our slope is 15. But here we're counting by 50, and here we're counting by 2s. The second tick mark is labeled 4, right? So wouldn't that each tick mark be considered 2? Okay. All right. So what can I do to end up with a slope of 15? Anybody have any ideas? Okay, what do you think, Luke?
Go in between the second line and, well, the line in between 12 and 16. Just go in between that and that line and 16, and that'll be 15.
Okay. So that would be over 15. But we want a slope of 15 over 1. So we want, how would we do it? We want whatever slope we choose to reduce to 15. What do you think, Rose?
Can't you just like go up a little bit and then go over like half the mark?
We could, but would it be very exact? No? Okay. Olivia, what do you
Can you
think?
change it to 30 over 2?
Can we change this to 30 over 2? Yes. Can we count up 30 real easy? No, but you are so on the right path. What could we change it to that would be easy to count? 15, can I do 50 divided by anything and get 15? No. Can I do 100 divided by anything and get 15? No. Can I do 150 divided by anything and get 15? Oh, it's 150 over what? 10. Is it easy to count up 150? Is it easy to count over 10? Yes. So even though this problem looks so easy, this counting out my slope is a real pain. So I'm going to go 1, 2, 3 for 150 and then go over to 10, and I'm going to have to move in front of y'all so I can do this. 10. Okay, there's a point. And I can do it again to get to the next point, can't I? Now, what is another way we could have done this instead of figuring out how to convert that slope? I can pick any x value I want on here and plug it into this equation and figure out a y value for a next point, couldn't I? Let's say I just plugged in the point 10. If I plug in 10, I get 150 plus 200 is 350. I can plot the point 10, 350. Oh, it's already there.
Oh, dang.
And draw in the line. Okay? Now, if I had picked anything else, it wouldn't be perfect. It wouldn't have crossed on the crosshairs nicely like it does there. But it would still work.
You could do 20 over 300.
Yes, you could. I could do 30. I could do 40. All of those would have worked nicely for me. Okay, now you try graphing the second one. And you pick how you want to do it, because once again, the slope isn't going to work for you.
Do that second method, 10, dirty clock, 50.
Okay, so on this one, if I plug in 10 right here, I get 100 plus 300 is 400.
You just use 10 for all. Can you use 10 for always? So,
No,
no.
it just works out nicely on here.
Okay. I think that's.
What'd you get?
740. 7 months, 4 months.
You got 20 months.
Oh, I'm in number 2.
Ah, okay.
I
Number
am-
2 is your homework. Yes.
We just write our answer, the balance in respect to months, but the numbers,
Okay, I would say
like
in
respect to
20 months, both accounts will contain $500. Contain isn't the right word.
Why don't you just say we'll have a balance?
We'll have a balance. I like that. Okay. For this one, you could have changed the slope to 100 over 10 because that reduces to 10. Or you could have plugged 10 in, and if we plug in 10, we get 100 plus 300 is 400. Either way, we get this graph. Now, if I were just presented with this problem and I was not told I had to graph it, there's no way I would do it this way. If I want to know where they're equivalent, because these two are the same, I would substitute this in right here and get this equation. Whoops. 300 plus 10m equals 200 plus 15m. So 100 equals 5m, and 20 is the number of months it would take them to be equivalent. So you can use substitution, just like we did in our warm-up today, to solve this also. Now, why is a graphic representation nice? Because if you have this graph, I could ask you questions like, when will account A have more money? Well, account A is my blue line, so it's any time after 20 months. You can ask other types of questions if you're looking at a graph versus not looking at a graph. Okay? All right, your homework is out of the workbook. It's on pages 101. You're to do 2 through 5. And on page 102, you're to do 2 through 6. Okay, I'd like you to do them the way they ask. If you get an approximate answer and you want an exact, then go back and use substitution. But today is asking you to focus on graphing. And if we go ahead and have that practice now, then next week when we start doing linear programming, it'll be much easier. Okay, I'm going to cut off the video and answer questions.